now we have definitions for velocity and for speed to add on to what we know about position, elapsed time, and displacement. So let's look at some simple examples. First thing I'm going to do is write down my definition of the average velocity, and then we're just going to look at all these examples individually. So I have my average velocity. Remember, it's defined as a displacement over an elapsed time. And this first problem says a particle starts at position x sub naught equals 1.7 meters and it's going to move to some final position 5.09 meters. What's the velocity if the elapsed time is 2.0 seconds? Remember when I said elapsed time in this example, that's just delta t. This elapsed time, that's delta t. So I'm going to rewrite this definition of my average velocity as delta x over delta t. I'm going to remember that delta x is just my final position minus my initial position, or x sub f minus x sub naught. In the denominator, I'm going to leave it as delta t because this problem gives me delta t. It told me that that was 2 seconds. And now I'm ready, with just a little bit of manipulation, to plug in some numbers and get an answer. So my final position was 5.09 meters. My initial position was 1.70 meters. Hopefully you can read that over those scribbles. For my elapsed time, that's just 2.0 seconds. So I'm going to plug all this into my calculator. 5.09 minus 1.7 divided by 2. And what I find is that my average velocity is just 1.70 meters per second. And I put that final answer into a box like that so I know that I'm done with the problem. This was a nice problem in that I didn't really have to do any algebraic manipulation. Everything was all lined up. In this next example, though, we're going to say this. How long does it take a particle with a velocity of 3 meters per second to travel 180 meters? So notice in this problem, I have that my velocity is 3.0 meters per second, and my displacement is at distance that the particle traveled. It's 180 meters. And so I write out V average, and in this case we're going to assume that this particle is moving with some average velocity 3 meters per second. So when I write out the definition again, average velocity equals delta x over delta t, I'll see that how long part of the question is asking for delta t. I just have to isolate that algebraically. So if I multiply through top and bottom by delta t and I divide through by the average velocity, the expression I'm going to get is this, that first delta t times V average is equal to delta x. That's me multiplying through by delta t, and it's going to cancel out on the right hand side. And then if I divide through by V average, I'm going to get this expression. Delta t is just equal to delta x over V average. I can plug those numbers in because I was told that delta x was equal to 180 meters. I know that the average velocity is 3.0 meters per second. Notice that those meters are going to cancel out in top and bottom. Because I have 1 over seconds in the denominator, I'm going to get a second in the numerator. Plugging that into my calculator, if I have to, is just going to tell me that it takes 60 seconds to travel that distance. And again, once you've isolated that final number, it's good to put it in a box, depending on how you're solving the problem, just to show yourself, hey, I've reached that final answer, and there it is. Now this is really common. We're going to have some definition like V average equals delta x over delta t, and you're going to be asked for some part of that. Not necessarily the average velocity, sometimes delta x, sometimes delta t, and you need to get comfortable with doing that basic algebra to isolate the quantity that you're interested in. And we're going to go with this thing one more time. Here we have a particle beginning at x sub naught equals 1.7 meters. We see it moves to some final location, x sub f is equal to minus 5.09 meters, and we're told the elapsed time 2 seconds. And here we're going to be asked, what is the speed of the particle? Remember, the speed is just the magnitude of the velocity. I'm tempted to write out my average velocity first and just say that's delta x over delta t, in this case xf minus x sub naught in that numerator. If I plug in these numbers, actually here, let me clean that delta up just to make sure that it's legible. Well, I'm going to plug in my numbers for x sub f minus 5.09 meters minus x sub naught, which was 1.70 meters. I divide through by 2.00 seconds. So I'm going to put the numbers into my calculator first. Bear with me for 1 second. And as always, check my numbers, but I get this. I had 3.40 meters per second with a negative sign in front of it for my average velocity. So I can't stress this enough. Always check these numbers, that you're given by the book or given by me. It's great practice for you. And sometimes there's going to be mistakes in the book. Remember, this is my velocity. Velocity is a vector and has magnitude and direction. Speed does not. The speed, and we'll just call this, the speed, is just equal to the magnitude of that average velocity, and that's just going to be 3.40 meters per second, and that's the answer that we wanted to find. I guess the trick here with this problem was just that we had a negative velocity, and so when you calculate that speed, it's always going to be a positive quantity. So hopefully these were good examples in exploring that definition of our average velocity and learning how to isolate each individual part of that expression.